Welcome to Algebra 1 with Miss Betsy. Today we're going to be talking about how we simplify radicals, and we're going to see that just as you always want to express a fraction in lowest terms or in simplest form, we need to do that very same thing when we're working with radicals. I'm using as my text the second edition of Algebra 1 for Christian schools. It's published by Bob Jones University Press. Make sure that whatever text you're using, that you can be tracking right along with the same sort of information. I'm on page 400 in this text, and I want to read just a little bit, summarize a little bit of what comes from your text at the very beginning. And fractional answers are always given in simplest form. Each time you have a radical in the solution to a problem, that's going to have to be expressed in simplified form also. And then it goes on and tells you how we know that a radical is simplified. It has no perfect power factors, means that if you're taking the square root of something, there are no perfect squares underneath the radical symbol. If you're taking the cube root of something, you wouldn't have an 8 left underneath the radical symbol, for example, because 8 is a perfect cube, and the cube root of 8 would be 2. You're also not going to have any radicals in the denominator, and we're going to learn about that in just a couple of days, a week or so, and it's called rationalizing the denominator. If you have 2 times the square root of 7 divided by the square root of 5, we're going to learn that that is not simplified form, and that it's not acceptable to have a radical symbol in the denominator. We're also going to see that you can't have any fractions underneath the radical sign also. Something that we talked about a long time ago when we were doing rules of exponents, rules of radicals, we learned something that was called the product property, and this is really important. And what it tells you is that if you take the root of some random number, let me make sure that I'm using the same letters they are, because I'm totally tearing this book to pieces. Nth root. If we're going to take the nth root of the product of x and y, some root of some number that is factorable, you can break that into the roots, the product of the individual roots. So what this says is the root of a product is the same as the product of the roots. In very general terms, this is like using expanded notation to express a number. 45 can be expressed very simply as 40, or as the sum of the tens plus the sum of the units in there. 45 is the same as 40 plus 5. All right? This is the general idea that we're using here. For example, let's say that we want to take the square root of, let me see what I want to do. This didn't plan this one ahead of time. 9 times square root of 36. Okay? We already know that the square root of 36 is 6, don't we? But let's pretend that we don't. See if we can factor this number here. See, right here we're showing 2 factors instead of a product. How can we express 36? Well, one way that we could express 36 would be to say that 36 is equal to 4 times 9. So the square root of 36, or the square root of the product of these 2 numbers, which is 36, is the same thing as the product of those square roots. When you have radical symbols bumped up right against each other, remember that indicates multiplication. Just as when you have variables bumped up against one another, that means a times b. This means the square root of 4 times the square root of 3. And what is the square root of 4? That's 2. The square root of, I think I said square root of 3. Square root of 9, which is 3. The square root of 4 is 2. The square root of 9 is 3. And 2 times 3 is in fact equal to 6, which is what we knew. The square root of 36 is 6. When this is going to come in very handy, this product rule, this is called the product rule. And this tells us that the root of a product is equivalent to the product of the roots. And this allows you to factor underneath the radical symbol into perfect squares, perfect cubes, whatever root it is that you are attempting to find. This is something that's very, very, very important to be able to do. So make sure that you understand that little fact there. And then a little tidbit extra that they put in this book is the fact that approximations are not accurate. Mathematicians like to be precise and accurate, so they're going to typically use simplified radicals to indicate an exact solution. For example, going back to section 10.1, if we wanted to find an integer approximation for the square root of 50, we learned that what we needed to do was to sandwich this square root of 50 in between two perfect squares. So 49 is a perfect square, which is less than 50. 7 times 7 is 49. 8 times 8 is 64. And we learned that we could say the square root of 49 is less than the square root of 50, which was also less than the square root of 64. Because we have this radicand here bounded by perfect squares. So we saw that 7, or that the square root of 50, comes somewhere in between 7 and 8. But this is just an approximation. And we learned that we could also put this number into our calculator, and we would see that the square root of 50 is going to be 7 point something. And because 50 is very close to 49, it might be 7.1, and then a bunch of digits that are going to carry on forever because they're irrational numbers. They don't terminate and they don't repeat. So you could say that the square root of 50 is between 7 and 8. You could use your calculator and come up with some decimal estimation of it, but mathematicians like to be precise, so they are going to use the simplified radical to express an exact answer. If you go back to the beginning of this section, it says that radicals cannot have any perfect powers underneath here, and this is where we're going to come into using the product property. We're going to look at that 50 and see how we can factor it so that it has some perfect squares in it. Well, right away, 50 is an easy one. 50 can be factored as 25 times 2. It can also be factored as 5 times 10, but factoring it as 5 times 10 is not of any use to us. It's of no use to us because neither 5 nor 10 are perfect squares, where 25 is a perfect square. And this is where we're going to use our product rule. Remember that said that the nth root of x times y was the same as the product of those two roots. The nth root of x times the nth root of y. So we can use this product property here to rewrite this as, rather than the square root of the quantity 25 times 2, we can say this is the square root of 25 times the square root of 2. And the square root of 25 is 5. So the simplified form of the square root of 50 is then 5 times the square root of 2. And I know that you're going to look at that and you're going to say, there's no way that that is simplified because it just looks weird. It does, but in the mathematical world, this is simplified 7.12, or whatever the simplified estimation of. This is not, because this is an approximation, whereas 5 times the square root of 2 is an exact answer. And this is the type of answer that we're looking for when we simplify radicals. So now let's go ahead and look at example 2, which says simplify the square root of 75. Very, very same thing that we just did. Square root of 75. You can look at that simply by inspection. And you know that 75 is equal to 25 times 3, and we picked that because it's valuable. 25 is a perfect square. Square root of 25 times the square root of 3. You can simplify the square root of 25. You cannot simplify the square root of 3. So our answer to this is 5 times the square root of 3. Now our example 3 says to simplify the cube root of 40. This is where simply being very familiar with factors will help you. Remember I said to make sure that you knew the first few perfect cubes. 2 cubed is 8, isn't it? Is 8 a factor of 40? Yeah. So we can break 40 apart into 2 factors where we have the cube root of 8 times 5. Use our product rule to say the cube root of 8 times the cube root of 5. What number used as a factor 3 times gives us 8? Well, that's 2. Is there some number we can come up with used as a factor 3 times that gives us a product of 5? Of course not. 2 times the cube root of 5, believe it or not, is the simplified form of the cube root of 40. And this is where you have to understand what's going on, because there's no way that your mind is going to say that this number right here, that this representation here is more simple than the cube root of 40, but in the math world it is, because you're not allowed to have any perfect cubes underneath that radical sign there. Now what I have written off to the side of the board here, this is a summarization of what you have written in your text at the bottom of page 400, which is called the general method of simplifying radicals. First thing that you do is factor the radicand into primes. Second thing that you do is you divide the exponent on each prime factor by the index. The third thing here tells us that the quotient becomes the exponent on the prime factor outside the radical sign, and the remainder becomes the exponent on the prime factor inside the radical sign. Let me show you what we're talking about. Example 4 says, my glasses are not working. Simplify the cube root of 3 times 600, the cube root of 648. Cube root of 648. Okay? Being dyslexic here. 648. I'm going to prime factor this. Right away I'm looking for something that I can break this apart into pretty easily. I know that it's going to be divisible by 4 because the last 2 digits here, 48 is divisible by 4. So I'm going to say, let me see if I want to do factor tree division. I have 648. I have 4, and I'm going to have 162. Let me make sure this is right. 4 times 2 is 8. 4 times 6 is 24. and carry 2. 4 factors into 2 times 2. 162 is divisible by 3 because the sum of the digits is divisible by 3. So I have 354, I think. 3 times 4 is 12. 15 carry 1 is 6. Is your factor tree going to look the same as mine? Maybe, maybe not. Doesn't matter. 3 is a prime. 54, 6 times 9 is 54. 2 times 3, and 3 times 3. I've now completed the first step. I have prime factored 648, and I'm going to write this now as a product of primes. So I have 2 cubed, 1, 2, 3, and I have 1, 2, 3, 4. 2 cubed times 3 to the 4th. This right here is the prime factorization of 648. So I have 2 cubed times 3 to the 4th. And I want to simplify this. What is the cube root of 648? What I'm going to do is divide the index on each factor, divide the exponent on each factor by this index over here. Okay? 3 divided by 3 is 1. That's the quotient. The quotient is the exponent on that prime factor outside the radical. I have this radical symbol, cube root of something. The first factor that I look at is 2. I divide the exponent of 3 by the index of 3. 3 divided by 3 is 1. So I'm going to have that 1 be the exponent on the prime factor outside the radical sign. We don't show an exponent of 1 though. So I have 2 on the outside. The remainder is the exponent on that prime factor inside the radical sign. Okay, well, what's the remainder? There wasn't any remainder. No remainder, so a 0 remainder. What's 2 to the 0? Anything to the 0 power is 1. So what it means is if your exponent on your factor divides evenly with your index, it's a perfect cube. There's not going to be any factor left over. 2 cubed is 8. The cube root of 8 is 2. There's no factor left. So we've taken care of our factor of 2. Now, the next factor we have is 3. We're going to divide this exponent of 4 by the index of 3. 4 divided by 3 is 1, remainder 1. The quotient is the exponent on the prime factor outside. It's a factor. 2 times 3. 4 divided by 3 is 1, remainder 1. The remainder is the exponent on the factor inside the radical. Remainder of 1. Again, we do not show the exponent. 2 times 3 is 6 times the cube root of 3 is our simplified form of the cube root of 648. Okay, I really, really, really wish that this next example here that they had done a different example. I'm going to go ahead and go through it anyway because it will illustrate how well this little formula works to simplify a radical. What they're asking you to do is to find the 5th root of this ginormous number, 14,580. And they went ahead and used upside down division or ladder division to find the prime factored form of 14,580. And you remember the way that you do this, or you can use a factor tree. Keep dividing by 2 until you cannot divide by 2 any longer. Then move to the next prime number. This is not a class on prime factoring. Okay, what we end up with, the prime factorization of 14,580 is, if I can make my glasses work right, is 2 squared times 3 to the 6th times 5. Now, what they have done is they've gone ahead and expressed some of these as fractional exponents. Let me show you what this could be. This would be 2 to the 2/5, 3 to the 6/5, 5 to the 1/5. Because what I have done is I've said, let's take the 5th root of this factored form here. 2 to the 2 squared times 3 to the 6 times 5. Okay? We want to divide each exponent by the index. Okay? This is just how we would express this in fractional form if it's helpful to you. So we are going to have the 5th root of something. The first factor that we're looking at is a factor of 2 squared. 2 squared, what are we supposed to do? We're going to divide the exponent by the index. 2 divided by 5. Well, it's 0 remainder. 2 divided by 5, you can't do it. Divide the exponent by the index. So I probably wrote this back. No. Can't do 2 divided by 5. You have 0 times 5 is 0, and then you have a remainder of 2, don't you? So there's no factor of 2 that goes on the outside. You have a factor of 2 on the index, 2 on the inside, with your exponent here of 2. Because our remainder becomes the exponent on the factor that's inside the radical sign. Now let's look at 3 to the 6th. We're going to take the exponent divided by the index. The quotient is 1, and the remainder is 1. The quotient right here of 1 becomes the becomes the exponent on this factor of 3 that's outside the radical symbol. I can pull this out here. 3 to the 1st. The remainder of 1 right here becomes the exponent underneath the radical sign. All right? What's our last factor here? We have a 5. Can you divide? You have a 5 to the 1st. Can you divide 1 by 5? No. You're going to end up with a remainder of 1 times 5 to the 1st. The only perfect 5th root that you had was 3. So you have 3 times the 5th root of 4 times 3 times 5, or 3 times the 5th root of 60. This is sort of awkward to do. Let me show you something else that might help you when you are looking just at these exponents. Erase this. I have 2 squared, I have 3 to the 6th, and I have 5. And what I'm going to, 5 to the 1st. And what I have here that I'm going to show you, we're allowed to do because when you multiply exponentials together, you add the exponents, remember? When you divide, you subtract the exponents. Okay, we're going to divide this number right here. We have to have 5 factors of 2. Or we're going to think, what does exponential notation mean? Talking about how many times 2 is used as a factor. 2 is only used as a factor twice. How many times does it have to be used to be a perfect factor, a perfect root here? We need 5 of them. We don't have 5 of them to use. So every bit of those stay inside the radical sign. We're looking for 5 factors of 6. When we use 5 factors of 6, how many do we have left? We have 1 factor of 3 left, don't I? And again, it seems like I said 6. We're looking for 5 factors of 3. We have 6. When we use 5 factors of 3, we have 1 factor left. That's where that 3 comes from. Now we're going to look at this factor here of 5. We need to have 5 factors. We don't have 5 factors. How many do we have left? We just have 1. So that single factor of 5 remains underneath the radical sign. So this right here, 3 times the 5th root of 60, is the simplified form of this big old mess right here. The 5th root of 14,580. Now example 6, we are going to add some variables in here. We're going to use the same principle of how many factors do we need to use, how many factors do we have left over to help us to simplify this expression. Okay, we have the square root of 32x cubed y squared. Square root of 32x cubed y squared. So let's go ahead and prime factor 32. Or you can simply break it apart into what you know are perfect squares. This can be the square root of 16 times 2 times x cubed times y squared. Okay? Let me go ahead and prime factor 32 out to the side. 32 is 4 times 8, 2 times 2 times 2 times 4. Okay? 32 is equal to 2 to the 5th. We're just going to keep that prime factorization over here to the right. Come back to it when we finish this. What's the square root of 16? Square root of 16 is 4. So we've already dealt with that. Can we take the square root of 2? No. Now, we're going to look at this x cubed. How many factors of x do we need when we're finding the square root? That's that index over here that we don't write because we understand that we're talking about the square root. But the index is 2. So we need 2 factors of x, or multiples of 2 factors of x. How many factors of x do we have? Well, we have 3. So I need to leave room for every multiple of 2 factors of x. That x comes outside here. That's where we're looking at the quotient. We're going to divide this exponent here by the index. The quotient, which is 1, is the exponent on this factor of x outside the radical symbol. The remainder, which is 1, is the exponent on that factor underneath the radical symbol. And again, now we have y squared We want the square root of that. 2 divided by 2 is 1. There is no remainder. The simplified form of the square root of 32x cubed y squared is 4xy times the square root of 2x. And in our minds that may look a lot messier than what we had here, but we have simplified this because you can't have any perfect powers in this case. You can't have any perfect squares underneath the radical symbol. Now I broke this apart into 16 times 2, but over here I prime factored it to where we had 2 to the 5th. And let's go back to this method for finding the roots. This was on page 400, and they called it General Method of Simplifying Radicals. You're going to take the exponent on the prime factor, which is 5, and you're going to divide that by the index, which is 2. 5 divided by 2 is 2 with a remainder of 1. The quotient becomes the exponent on the prime factor outside the radical sign. So this prime factor here is a 2 with an exponent of 2. What is 2 squared? 2 squared is 4. The remainder is the exponent on the factor inside the radical symbol. That's where we end up with this 4. That's where we end up with the 2. Okay? I know you can do this. It's a little bit challenging. Actually, it can be a lot challenging until you are accustomed to what you're doing. And it's going to take some practice, but I know you can do it. Okay, example 7. We want to look for what is the square root of the quantity x plus 2 squared. Very important that you understand what we're talking about here. We have the quantity x plus 2 squared. So what does that mean? This tells us that when we have the quantity x plus 2 in parentheses squared, that this expression x plus 2 is being used as a factor twice. So this factor, x plus 2, that's a right of 1, x plus 2 is the answer. It's all that's involved in this. We can follow this same pattern here. We're going to divide the exponent, which is the 2, by the index. 2 divided by 2 is 1. That's the quotient. Becomes the exponent. Quantity x plus 2 to the first is simply x plus 2. Chew on that for a bit until it makes sense, because we're going to use this principle over and over and over and over and over when we're factoring and when we're dealing with Algebra 1 and on into Algebra 2 and pre-calc. Last example that I want to show you is example number 8. Hang in there, we're nearly done. We want to simplify the cube root of 16x squared y to the 4th z to the 6th. And here they are going through and translating this into fractional exponents. This would be not even worth me showing you. Okay, I'm not going to take the time on this video. Look at what they've done. It's of value for you to be able to figure out what they've done. But I want to go ahead and show you another way that they are illustrating what's going on. This is 2 to the 4th times x squared times y to the 4th times z to the 6th. And let's just go ahead and break all of this down. Remember when we were learning how to use exponential notation as repeated multiplication? this is really the cube root of 2 times 2 times 2 times 2 times x times 4 factors of y times 6 factors of z. And seeing how this is stretched out here is a good reminder to us of why exponential notation is so very beneficial. Looking for my black marker. And I have no idea what I did to it. Okay. We're looking for perfect cubes, or perfect triples here. So we have this triple here. We have this triple. We have triple z's twice. Perfect cubes. Perfect cube of 2 cubed is 2. Cube root of something. We've already used this. Perfect cubes, we have to have 3 factors. We have 3 factors of y. 2 times y. Perfect cubes, we have triples. We have 3 factors of z here. Cube root of z cubed is z. We have another grouping of 3 factors of z, so it becomes z squared, or z times z. Now, what do we have left inside? We have a factor of 2. We have 2 factors of x. We have 1 factor of y. And we've used up all of our factors of z. Now let's use exponential notation. 2yz squared times the cube root of 2x squared y. Let me verify that. 2yz squared cube root of 2x squared y. Okay? Cube root of 16x squared y to the 4th, z to the 6th is this right down here, 2yz squared times the cube root of 2x squared y. This doesn't look more simple, but it is because you're not allowed to have any perfect cubes underneath the radical sign. Let me, now that I've shown you this method, let's see if we can get the same answer just by looking at the exponents and understanding what we're doing. We're going to be finding cube roots. So if we need 3 factors of 2, and we have 4, it means we have 1 cube outside, and we have 1 factor of 2 left over. What about our x's? We have to have 3 factors of x. We don't, so everything stays inside. We have to have 3 factors of y, which we do. So for every, the cube root of y cubed is y. So we've used 3 of those factors. We have 1 left because we started with 4. Now we have z to the 6th. 6 divided by 3 is 2. We have 2 sets of triples. So we have z squared, and there are no factors of z remaining. And you see that we ended up, of course, like we have to, with the exact same answer. You can also arrive at this answer using fractional exponents. Go ahead and investigate that, work on these problems, and if you need some help, send me a text or ask me in class on Friday. Thanks, I'll see you next time.